Many fleet assets like locomotives, aircraft, and military weapon systems generate a lot of data. As we've previously discussed, fleet asset lifetimes typically span decades, and a large portion of the world's fleet assets have outdated onboard technology. This provides a major opportunity to run more profitable, safer, and smarter operations by upgrading fleet assets with modern technology. Data science is an interdisciplinary field related to data mining, machine learning, statistics, and big data analysis. It focuses on extracting knowledge from typically large data sets to solve business problems. In this episode, special guests Ellie and Dan Morton discuss how we can apply data science principles to fleet data to make fleets smarter and safer. Ellie is the product lead of anomaly detection and data science at Shift5. Her focus is aligning analysis with scalability and impact for customer data sets. She comes from a background in applied cryptography, secure protocol design, and industry research for emerging technologies such as quantum and private computation. Dan Morton is a data scientist at Shift5. His focus is on solving real-world customer problems with data. He earned his PhD in particle physics, searching for rare events in large data sets. Dan, Ellie, welcome to the show.
Thanks for having us.
Great. It's great to see you. I am super excited about this topic. I think when people look at fleet assets like locomotives and aircraft, as we've talked about on the show, they don't typically think of these as giant pieces of technology that are throwing off tons of data. But in fact, they are. And we can apply some of the great inferential techniques that we've learned in the data science fields like data mining, statistics, machine learning, and AI to these things and get some pretty incredible results. So I'm super excited to talk to you guys. I think maybe for a general audience, we could sharpen up a couple of key concepts so that we can circle in on what exactly we're talking about. So maybe let's start with a simple one, which is what are fleet assets?
So one of our focuses at Shift5, of course, is like transportation. So if you think about a train fleet, maybe, the fleet assets are just like the actual locomotives that are kind of a part of this like group of technology, whether the technology is kind of on the like, I don't know, tech side or the mechanical side, right? Just anything that sort of makes up the items that are like driving business for a big system. So in transportation, maybe locomotives or like tanks or whatever.
Logistics, you have trucks or trains as well, possibly even aircraft. So all of these assets which are then used which assemble, as the name implies, fleet or a large group of these vehicles and the things used to directly support them.
And I mean, these assets predate the transistor, right? You think about Ford's Model T, the locomotive. These are storied features in American history. Why do they have so many computers in them now if they were working for decades before the advent of the transistor?
So that has a lot to do with actually being able to control very clearly what's going on within the devices, being able to monitor it and make these systems more efficient. Over time, of course, the other issue is with analog systems, you need a million specialists, and it becomes much simpler to have everything running on certain protocols. Just becoming a digital device which you can control and throw commands in between things. So it actually simplifies who and what you need in terms of resources, and it also improves efficiency down the line and all these other issues. All the time, you have analog systems which have a tendency to slowly wander off their baselines and start throwing off incorrect things and other issues like that coming up, while these digital systems make it very easy to control, monitor, and do things like that. And in fact, I would say this isn't completely unique to vehicles. This has been true for a lot of devices which rely on the same physical principles that they did 100 years ago. And maybe this surprised a lot of people, or maybe not, but even if you think of like your dishwasher or something like that, what's different about it is there's a computer in it now, right?
My favorite example is like the smart toaster, right?
Yeah. Oh, man.
You never knew you needed it, but once you have it, how could you live without it?
I think the other like interesting thing, like Dan kind of drilled into operating things, but I think just flipping to like user experience, that's another like very important implication of adding these digital components to like traditionally non-digital systems.
Yeah, so it's economic reasons. The manufacturers of these devices can make things that are more reliable, more flexible, more robust, with a more general purpose labor pool, like you were talking about, Dan. And from a user perspective, the allure of having electronic components allows you to have way more featureful interfaces and add a lot of convenience to things, right?
With less like domain specific knowledge required, as Dan had kind of alluded to
right.
also.
Right. Yeah. I mean, I think additionally, we've seen even a renaissance in electronic components with respect to who can program these things and who can design these circuits, because for a long time, hardware was the domain of hardwired circuits and transistors and integrated circuits that have very specific input outputs. And then we talked about this, Ellie, a couple of weeks ago, but microcontrollers, these reprogrammable integrated circuits that run software, are all over the place now. They're super cheap. For a couple bucks, you can put a microcontroller in place of dozens of integrated circuits. And now you have software engineers that can program hardware. Of course, it's a little, embedded circuits are a little more complicated, dealing with real-time operating systems and things. But in principle, you have people that are writing C rather than, designing circuits in KiCad or something like that. So I think at many levels, these things are becoming more and more accessible to different pools of labor. So we see this landscape of digital components getting integrated onto these fleet assets, into our kitchens at home, all over the place, right? But these things tend to happen by degrees, right? You see model years of cars integrating more and more electronic components. All of a sudden, they're fly by wire now. All these cars are fly by wire, where 15 years ago that wasn't the case, right? But one thing we've commented on often in this podcast is that no one really thought about where we were going by packing these assets full of digital components. And so we've gotten to this place where, there are tons of digital components in these systems, but they weren't designed from first principles for the digital age. And so we've talked a lot about what the cybersecurity implications of that are, of which there are many. I think in this show, we're going to focus more on, okay, well, there's some doom and gloom out there about how all these systems are just totally vulnerable, and the only cybersecurity they have in them is physical security. And we know how dubious that is. But instead, now I think we have a real opportunity, because these, Dan, you alluded to these things having congealing around protocols and throwing off tons of data. So these things are talking to us. It's just that in a lot of cases, we aren't listening. We're not collecting this data and using that data for operational and maintenance purposes. That could help you run your business more efficiently, or operate a metropolitan passenger locomotive service more safely, because the assets are getting maintained. But these assets are around for a long time, right? Like decades and decades and decades. So I guess one question that I think a lot of people have is, well, if you've got a decades old locomotive, sure, it's got digital components in it, but it's sort of stuck, right? Like how can you retrofit these things to bring them into the 21st century?
I mean, part of it you alluded to before, but like the data is already being generated, right? All we have to do is kind of tune in and listen for it. I think part of what's really powerful about doing that data collection is that a lot of times, like I know a couple of our customers, at least, these are things that they've never had visibility into. And so it almost like takes them a couple of iterations looking through the data set to really understand, like, oh, like all of this is available to us. Well, that can help me do X, Y, Z. So I think just like providing visibility and grabbing what's already there and kind of marrying that with like insights that we may have available on like newer systems, but not older ones.
I think it's also important to realize when systems actually became digital at all versus analog. And you're talking about more 70s, 80s era is when most of these things switched over to a digital bus of some sort. Yeah, you're not going to be dealing with the same speeds or density of systems nowadays, but you still have digital data. And that's the important aspect versus a completely analog system. So almost all of your industrial hardware, your I think PLCs, as they're called, devices like that, are still communicating through digital means. So you're still controlling that way. So in fact, we really need to do to access that and give people access is to tap into it, right? In many ways, we have a pipeline, we have a flow going on. There's this flow going on in your device, and it's almost like adding in a tap where you can take a sample and see what's happening.
And how hard is adding a tap to these systems? I mean, are they designed in a way where that's really difficult to do, or give me a sense of in general how hard that is?
Yeah, usually this is not hard at all. A lot of times, like if you think about cars, for example, they have CAN buses in them, and CAN is a broadcast network, right? So all we have to do is like also listen on that network, and we can see kind of everything that all of the devices are already seeing.
Yeah, a lot of these systems were designed around open standards, right? Like heavy equipment. There's the SA Society for Automotive Engineers J1939, which sits on top of CAN, and the express purpose is, hey, if you're going to design a component that interoperates on the CAN protocol, use this message format when you're reporting this quantity, because it allows you to interoperate with all the other stuff that's on there and sell your product to OEMs that are going to integrate these onto platforms. I mean, it's like we were talking about the thing that makes these buses so vulnerable from a cybersecurity perspective is also a huge opportunity, because all of this data is unencrypted. It's all available on the bus, and it's all there for you to just sort of sit and collect.
Yeah, and I think the standardization especially makes it a lot easier to like build analytics, because you kind of don't have to make something that's like bespoke for every type of message anyone could ever think up. But I also think it's kind of extra exciting when you think about combining, like Dan was talking earlier about analog versus digital means of communication. And you don't have to focus your analysis on just one, right? Like you can combine as many of these, or like multiple digital, multiple protocols, for example, or like a combination of analog and digital to sort of like coalesce everything to something meaningful.
Great. So the idea is it's not terribly difficult from a conceptual perspective to tap onto these buses, collect the data. In a lot of cases, you have readily available telemetry paths like 4G LTE or 5G, or you have Wi-Fi that's available, or Ethernet if it's like a sort of static platform that isn't moving. So you can pull all this data back. Let's talk a little bit about what do you do with that data. So there's some simple data engineering things, of course, right? You can take the data and you can aggregate it and build queries that are important, alert based on some rules. What are some examples in the locomotive industry that you guys have seen where simple aggregations and queries have delivered real value and solved problems for customers?
So right off the bat, one thing that was solved in the past, so before me, was finding engines which were idling for far too long. And some things that we're looking at now, which I think will be quite easy to find, are issues such as, there's one issue that I was thinking about because it's related to something I've done or had to deal with in the past, is where the brake lines have this tendency the air brakes have a tendency to get clogged up. Now, one thing that occurs when you have any sort of system that's getting clogged in some way or another is that the motor, that the pieces that are interacting with it they're actually running the air brake system itself, applying pressure and things like that, all function differently when that occurs. They have to work to different degrees, essentially, after that, depending on where they exist in that line. And so what you should see happen is some characteristic functions that will begin to come out and change. Now, right now, a lot of these engineers are used to popping systems open or there's a catastrophic failure. The system goes offline for a huge period of time. You lose millions, and that's how it works. But instead, if you can just clean out pop a system open and know when to clean it out because of some weird weather or something like that occurred, then you might be able to do that. And what we should be able to identify is these responses, aggregate these different responses from different pumps, which in some cases will only appear as changes in voltages, right? Something very small like that. But by looking at this large multidimensional system where we have all these information and knowing where a failure has occurred, we should be able to eke out and give a warning that's very clear to an engineer, hey, this needs to be done. Or else, yeah, the system is going to break down. And you know what? You don't want your air brakes to break. It's why everything shuts down.
And not only is it a safety issue, but when you run these things until failure, oftentimes the repairs are going to be far costlier than if you do preventive maintenance on it, right? So, Dan, is this an example of data science? And what is data science?
So, data science. What's fun about the term data science is it's still evolving, I would say, as a field, and still defining where it is and where it begins and where it ends. But in general, you're dealing with you're performing data analysis on large sets of data where you're trying to derive interesting relationships, build models to characterize it or glean insight from these very large sets of data. So where does it begin and where does it end? Well, because it has a lot of crossover with your basic data analysis, statistics, and machine learning, and that sort of end of computer science, because a data scientist is going to be building models, experimenting with brand new machine learning techniques, trying to build them in new ways, like machine learning, like somebody who might have the title of machine learning engineer, like that. But we're also going to be focused a lot more on sort of the mathematical insight behind what's actually driving these relationships within the data itself. So it's still at a stage where things are evolving. We might have a more clear definition, clear cut 5 years down the road as data science branches off into multiple fields per se. Because right now, sometimes it's used as a catch-all, but I like to see it as sort of this higher level study of these very large aggregate data sets, which are very large in scope, where you have a lot of different variables. So like I said before, you might have a huge switchboard of 30 to 100 variables in the training data set. And then we're trying to use techniques in order to actually really gain human usable insights.
I think a lot of it, I don't come from a data science background, and kind of learning about it and being in kind of settings where it's super useful to me, it's like the data science kind of brain is able to pick and choose what types of statistical techniques, I guess, should be applied to a certain problem, and combining them in different ways to kind of get the best performance or the best outcome or whatever from a certain scenario.
It's such an interesting question to me, because data science can mean so many different things to so many different people. And one of the, along the lines of exactly what you guys are saying, one of the ways I've heard it described is, there are basically three components that come together in a Venn diagram. You've got computer science, the ability to program your intent into a computer, subject matter expertise about whatever the problem domain is that you're trying to solve, if it's cybersecurity, if it's maintenance, operations, optimization type stuff, if it's, geology or whatever the subject matter is. And then a grounding in what is essentially derivatives of probability theory and mathematics, right? So understanding statistics or machine learning or AI or measure theory or whatever thing you're into on the probability and modeling side. And to your point, Dan, I think it's all about problems of inference. We have this inferential question: are the brakes going to break? Which locomotives are at idle by accident? There are these questions that involve uncertainty, and the role of a lot of data science or people that practice statistics or machine learning or data mining is to answer those inferential questions with a repeatable kind of piece of software and a whole lot of data, right? And it's fascinating. To your point, Dan, I think all of these things are evolving so quickly, and for people that want to get into data science, there's so many entrees into this field, and I feel like the evolution of Python and that ecosystem has really made it much more accessible to a broader range of people. I know when I was in grad school for statistics, we used R, right, which is kind of like it's a language only a mother could love.
Definitely not as like a quick, not as easy to come up to speed on as Python.
It sure isn't. No, it sure isn't. And Dan, you now when in your theoretical physics days, what was it? It was called Root. Is that right?
Yep, it was experimental physics, to be fair.
Experimental
but it was
physics.
Root, which was output by CERN. It's also actually being slowly. So at least people are going to disagree with me back and forth about this, but I know University of Michigan, for example, is phasing out teaching Root and C++ as its main course for Python, but it was an interesting take on. It's made improvements, but it was an interesting take on an interpretive C++ based language, which had all sorts of fun aspects to it, making it which can make it challenging to use or understand right away, but it was still very good at handling at the time large amounts of data. Back when the CERN was the largest producer of data in the world, right? There was a time where it absolutely had the highest amount of data coming in, and that's now been dwarfed by Silicon Valley. But it did great for what it was trying to do and put things in certain trees, but it definitely made a lot of things much harder than they had to be. And when I go back to it, it's just like, okay, well, I'm kind of glad I'm moving on from that.
Yeah. I guess the amount of Twitter likes and ad clicks are rapidly subsuming the measurements of subatomic particles, which we can comment on whether that's a good or bad thing. I think it may be another show.
Yeah,
that'd be a good different conversation, but a good one too.
Yep.
It's just and what it comes down to is, especially when you're dealing with something like what CERN was trying to do and deal with some of these tools and make them on their own, all the stuff. It still produces sort of open source environment. I think that's really important, and I'm glad it came up with computer science, and that's what makes it accessible.
Awesome. I totally agree. And so I think that's a really good overview of kind of data science 101 and the sorts of fields that circle around this concept of data science. Thinking about now this narrative thread of, hey, the fleet assets created an opportunity for us to collect a ton of data because of all the digital components in them. We're collecting this data now. There were some simple problems to solve based on, just queries and aggregations, the data switchboard. I like that term, Dan. Now, maybe we can talk a little bit more about where we see things going. What are the opportunities that the more sophisticated data science approaches give us with fleet data? What are some of the categories of things that fleet operators and owners can look forward to over the next couple of years as data scientists start unlocking the data that's in their assets?
So I think right away, one of the things to immediately note about this is that this is a very fertile field, essentially. So a lot of people haven't had access to this data. So there's actually a lot of room immediately to find things.
Yeah, I think one of the kind of immediate exciting opportunities is just operational kind of visibility and operational intelligence. Just giving like fleet operators awareness into what's happening in their systems, but also being able to optimize from there. So I think one of my favorite use cases to kind of talk about with customers or just at all is kind of the ability to understand emissions a little bit better and like what are the impacts of a fleet's like operations on the environment and kind of how can we measure that? Can we forecast it? Like are certain parts of the fleet doing better than others? And if so, why? That's one of my favorite use cases, but of course there are other things like maybe, I don't know. I think just kind of being able to reduce costs or make sure that you're kind of maximizing your schedule for ridership, something like that. Just a lot of like operational tweaks that could happen to kind of make sure that you're being cost effective, but also you're kind of providing a good experience for your customers and maybe being good to the environment or whatever other output you want.
For sure. Yeah. I mean, I think One of my favorite examples was what you brought up, like fuel efficiency and starting to incorporate greener fuels into what locomotives are using for power. And it's hard to answer the question of like, well, let's try this different fuel mixture or these additives and answer the question of, did this move optimize the thing we're trying to optimize for without collecting data? And so just the ability for people to run experiments, these like, what they call in this industry, like A/B tests, right? You run for a certain subset of your customers, or for, in this case, your fleet. You try something different. And because that's sort of like control and experiment group, you can see whether it made a meaningful change to the thing you care about, and whether that meaningful change was in a good direction or a bad direction.
Yeah, I think like to that point, a lot of at least emissions things are reported now on like a yearly basis. And just the fact, like, I don't know, it's literally mind-boggling to me that we can kind of give real-time awareness to this, to something that the granularity has been like measured in years, and now we can hand it to them in like minutes, right? And this data was there the whole time. All we had to do was kind of plug into it, right?
Yep. I think maintenance is another one. So simple data pipelining has solved so many problems for our customers. Like, oftentimes these digital components will actually throw error codes. You think about the check engine light in your car. There's an analogy to that in like engine control units and braking systems on these platforms, where they're saying, hey, something's wrong here. Like, I need maintenance. Please come check it. But for a lot of these fleet assets, there was no way for the maintenance section, or at least there's a very manual process for the maintenance section to understand that condition on the asset and put it into their repair and ticketing system. Whereas if you're streaming this data off, you can automate that entire ticketing process, and within a minute you generate a ticket and get this thing fixed.
And you can kind of trace. Sorry, Dan. You can kind of trace back root cause, right? Like, not only can predictions be made or like automating kind of maintenance tickets, but being able to really nail down what caused something is, I don't know, requires data. And that's something very powerful to give insight into.
Absolutely, it does. Unique, because a lot of times when you are trying to figure out what the root cause is, sometimes you'll just see error. A bunch of different errors are occurring. You need to keep doing fixes. Sometimes it's the same underlying root cause. Cars have a lot of analogies with this. If your shocks are shot, you're going to start getting some weird errors over time, because you're going to get loose wires and all these sorts of issues. And what you're going to see is these errors keep repeatedly happening. And perhaps on a previous vehicle was the shocks that started going bad. And that's great. That's a great model. But sometimes, when you don't have a ton of data, you can still make good inferences from what you do have in seeing, okay, everything's connected to one system, and then what system is that seems to be causing all these issues? What's that root cause? Absolutely.
Yeah, the context is really interesting, right? To do root cause analysis and sort of post hoc analysis. The other thing, Dan, that you alluded to is sometimes when you synthesize all of this data together, techniques like statistical process control and nailing down a particular measure that gives you the power to determine a maintenance condition that maybe didn't throw a maintenance fault, but you're able to say, hey, this engine is operating at a higher RPM for the same torque as the other engines in this fleet. We think there might be some sort of fluid issue in the engine, like you need to go take this in early for maintenance, or maybe based on GPS location, that an aircraft has been landing on semi-improved roads a lot, and that means that the certain components, which when you land on semi-improved surfaces going 200 miles an hour, it's going to cause a lot more wear and tear, and you need to bring that thing in for maintenance earlier. The electronic control units may not tell you that stuff, but you can tease that out if you've designed good models based on the ancillary data that's available, right?
Yeah, absolutely. You can definitely start beginning to, and some of the stuff at the lowest level are things that people are sort of aware that you can do to a degree, or maybe not the engineers working on them themselves or anything like that, or they might have an idea about it, but it hasn't been done for a large part because some people haven't been, I guess, there hasn't been as big of motivation for certain devices when you can open things up. But until people actually see the value that you really unlock with by applying these techniques. So I was in, for example, back in physics days at Fermilab, we were sort of forced to use some of these techniques, even when we didn't want to, because we had a big particle accelerator beam coming in. The area is radioactive. You don't want to touch things, so you instead have to rely on whatever you're getting in for these pressure sensors. And then over time, what you actually find is once you start actually aggregating your pipeline and beginning to identify these features, you actually really begin to save and can begin to see these things far in advance in ways that are actually impossible to do without constantly paying attention or anything like that. It's like one of the things that's great about computers is they don't fatigue and they're reliable in the same way. They're going to keep reporting and you always have an eye on this stuff. And that really changes things and changes your chance of catching things by orders of magnitude. And you can really begin to run your operations fundamentally differently once you begin to start doing that.
Yeah, because you have much more granular understanding of what's going on. You're operating with less uncertainty, and so your sort of risk reward trade off changes quite a bit, right?
Absolutely.
And I think what's also so fascinating to me about this space of operational technology data collection is what you've articulated, Dan, is really anomaly detection, right? In a lot of ways, a lot of these resolve down to, okay, we have a baseline for what normal parameters for a platform or a piece of OT should look like. These are the sensor data readings or functional groupings of measurements. This is what this should look like. And then when there are deviations from that baseline, we take action. The inference problem is, does this thing need to get fixed? Or do we need to make an operational decision based on the way that these things are operating? And that is not very different from the cybersecurity use case, right? So, Ellie, this is something you live and breathe every day, is thinking about ways of, okay, well, how do we assume compromise and have defense in depth and look at a signal, which could be the way that an endpoint is running, the processes that are on a computer. It could be the traffic that's going over the wire. It could be net flow data. There's all these different measurements that you're taking from the system. And you look at those measurements and you say, whoa, based on everything I know, this is deviating substantially from the baseline. We think that there may be an intrusion on this piece of equipment. Let's go do an incident response. And so I think for one of the first times in technology, what you're seeing is where kind of anomaly detection on IT networks didn't really make a big impact on business decisions, like the fact that employees came in at 8:30 versus 8:45 or logging in to different IP addresses. Like that doesn't really make huge operational impacts on a business. But it sure does when you're talking about a locomotive or you're talking about a piece of equipment that's generating widgets on an assembly line that is the core competency of a business. And so because of where we're collecting this data from, these operational technology assets, all of a sudden, I think this is a new frontier of like data science, of looking at the confluence of cybersecurity and operational intelligence coming from the same stream and using very similar techniques to just essentially tease out anomalies from what we're measuring.
Yeah, I think there are a couple of things that are interesting here. On one hand, I think in the IT world, especially in just like TCP/IP networks, there are a lot of things that we can do that are like probabilistic measurements, and it's still probably fine. And so what I mean by that is like, if we kind of take this measurement and it's right like 90% of the time, that's good enough, right? I think that's not necessarily the case in OT, right? Like a lot of these are kind of critical systems, critical infrastructure, and we can't, like 90% is not good enough. 99% is probably not good enough, right? Like we need those 5 nines or better.
For false positives.
Yeah, exactly. Yeah. But I think it also begs the question of like, there's kind of the philosophy of like garbage in equals garbage out, right? Like we have to A, be able to collect the data, but B, make sure that we kind of have a framework around the data that will give us the outputs that we want. There's one book that I know of by Danette McGilvray, and she kind of talks about dimensions of data quality. And this is like, it's not just her talking about it. I think she does a great job like distilling it into one book, but these are principles that we see everywhere, right? Like we need to make sure that our data is accurate. We need to make sure it's consistent. We need to make sure like it's easy to access. Is it relevant to the problems we're trying to solve? Is it like duplicatable, right? Like do we see it across the whole system? And so kind of just making sure that we have this full picture in a way that will give us like a good false positive rate so that we're not kind of providing bad data to infrastructure that's critical. And making sure that we can like continuously learn from this, right? And improve our data science as we go. I think those are kind of the big things to me. Like the problem is a little bit more, I keep saying critical, but it is like we need a little bit better kind of accuracy in the OT space, I think, in a lot of settings, maybe not all. And then we just need to make sure that like we're thinking about this garbage in equals garbage out problem and viewing like the whole data ecosystem.
Yeah, I mean, I think it's an excellent point that false positives need to be contextualized. Like, what is your appetite for false positive? And in IT, like if it's a cybersecurity setting, if you're not able to download an attachment from an email or access a website that you need to get to, it's annoying. Like it can definitely have impacts on your daily operation. But like if you accidentally drop a packet on a mission critical bus on an aircraft, like people can die. You know, we look at the Boeing 737 MAX 8 crash. This was a nose cone sensor that had a false positive or was generating data that was erroneous. And the MCAS system took over the autopilot to keep it out of a stall condition, but it wasn't in a stall condition. So it just like, you know, kept putting the aircraft in a really dangerous spot until it ultimately crashed. Right. So
I was just going to say to your point, that kind of begs another question that I think is really interesting. And like the data science meets like automation space is we can provide these insights, but like to what extent do we want to make the decisions for the person, right?
Right.
So I don't know. That's another like interesting question that comes into play and is like especially important in these kind of critical scenarios.
Absolutely. I have another analogy that's being considered in the health space right now. Just going back to more general data science, Bayes rule kind of things. One of the things that's being reconsidered, for example, is how is cancer testing and false positive rates, how often you want to do that? Because we're beginning to hit the point where they believe that a lot of the mental and psychological tools that's being applied to people in many cases are actually finally beginning to outstrip the advantages of catching potential cancers earlier on. So decreasing testing. And then the other damage of people if you give too many false positives, people stop believing them as well. You begin to undermine your own purpose. So that's always a careful balance that you have to strike in doing these sort of valuations. That's can be very tricky. And then when you're dealing with these you start dealing with super rare events, it becomes very hard for our brains to really contextualize them, like with numbers that way off your normal baseline. So that's always an interesting place to deal with and try to manage and make decisions because you can almost always guarantee improvement in some direction. It's hard to actually know what sort of the net gain you're actually providing is.
Yeah, and Dan, you brought up a really interesting discussion within data science communities, which is like the role of Bayesian statistics versus more frequentist approaches to solving inference problems. Could you dive into that a little bit and give us a sense of what the high-level argument is and where those tools may or may not be appropriate? I know this is sort of a religious war among statisticians, but...
It is. It's a different rule, though, in physics because of quantum physics. So in Bayesian statistics, for those who don't know, you have something called a prior distribution. you sort of are coming in with, this way to put this, in a sort of an assumed mathematical function or form that you can base what you're doing off of, and then manipulate toward in these different directions. Frequentist statistics basically say, okay, you need an underlying true distribution. In Bayesian statistics, you can have a probability distribution of bouncy balls on the moon acting in different ways. That's a nonsensical question in frequentist statistics because that hasn't happened, nor will it probably ever happen. It's sort of nonsensical to make conjectures on it. Now, in general, when you're dealing with things like naive Bayesian models and dealing with Boltzmann machines and things like that, I would say that your machine learning is sort of drifted pure into sort of accepting Bayesian statistics in general. And that's not too surprising given some of the underlying models that people base or inspire these systems in some ways are Bayesian, because I would say quantum physics is entirely Bayesian. It says that the reality is fundamentally Bayesian. You have a probability of bouncy ball quantum tunneling to the moon. Now, granted, you're not going to be able to express that with normal numbers because it's so low. You would need to do something utterly ridiculous, like exponential power 3 stacking them up. But it's there. But there is an argument to be made, and I would say that you need to, I would definitely say it's about judging the problem that you're dealing with, and understanding sort of the role of empiricism in making conjectures and what you're trying to do. It definitely, in a weird way, I would say it also matters for things like policy a bit more when you're trying to go forward with these things, because some people do see modeling things off of a prior as, and it can be argued as sort of you're not really following empiricism that way. So there is definitely a religious divide in statistics, but in practical application, I would say it's a little bit less so. And I think when this is where you see some of the statics of computer science come in, where they come from a space where experimentation is very fast, right? And so people who I know who are in that or taught me, learned from, definitely take the role of, okay, no, if you have an idea like that, you go out, you just need to try it and go and experiment. If it works, great. And that's a different philosophy, completely different philosophy than even statistics in general. So, and in a lot of sciences.
Yeah, I mean, it's a kind of a variation of the scientific method in some ways, right? Like you're supposed to. Yeah. I mean, like, rather than saying I have a hypothesis about this, I collect data and I'm going to make an inference about whether there's evidence for that hypothesis or not. You sort of have some prior belief about the state of things. I have a prior belief that this break might be, there's a 60% chance this break is in a state where it needs to get maintained. Given that, I collect some data and then I update my belief, right? And so just different kinds of models for different kinds of problems. To your point, it's really important that when you're trying to solve a problem with data science, with these models, you pick the right model. But it's also important, to your point, Ellie, that you put good inputs into that model. Garbage in is definitely going to yield garbage out. And so there are some challenges with getting good, clean data off of these systems, right? I mean, we spend a lot of time with some of these systems, reverse engineering protocols and building the software that translates the bits and bytes on the wire into something that people and algorithms can understand. What other kinds of data pre-processing do you typically see in data science in general? And then, maybe a couple of examples for fleet assets.
So in data mining in general, I mean, most of, I would say, data scientists' work in overall is going to be cleaning the data. You're going to get a lot of, so the fact is, with your data, you always have a lot of garbage. And a lot of times you have to make sure that you're dealing with that garbage. So some of the simplest examples are when you have somebody submitting data, but they didn't sanitize it. That's an age-old example, right? You'll run into it on forums all the time. Somebody's trying to save a JSON file with it, or CSV, and then they have commas and spaces all over the place, or tab separate. I've had some of the worst luck with some of these weird tab separated files. And this was by a professional company, but I remember having to derive sort of a formula to try to figure out exactly what combination of characters were input at this point, because it clearly was saved, modified, and saved again a few times. And so we had some rule of like, okay, when there's 6 spaces in a row, it was actually a tab mixed up with an incorrect character at the start.
You need like data science to sanitize the data to put into your other data science algorithms. It's just turtles all the way
Very meta.
down. Yes,
yeah.
Very meta.
But in terms of what we're doing, a lot of it's about trying to understand, I'd say, the underlying protocols and what's actually being said, because what you can deal with just pure data streams and try to make conjectures on that. But what's even better is if you actually understand what they're saying or trying to say.
I think part of that in fleets, not even like specific to fleets, this is kind of all technology, but we talked a little bit earlier about specifications. And so for a lot of protocols, there is like this open source specification that defines like exactly what the messages should look like and, how many bits are kind of saved for each portion of that, which is awesome, but that's on paper and that has to be implemented and it doesn't always get implemented exactly to spec. So kind of sussing out like, okay, what is this supposed to be? What is this trying to say? Like what parts of the specification map to the actual like implementation can be another challenge, and just trying to make sure that all of that is like mapped to the correct thing to feed into data models can be a challenge.
Especially when you're just trying to read off data, you're expected to follow a certain format and something in there doesn't follow that rule. Very common, and because usually, you have a general open form, which most things you're going to follow, but then you almost always have proprietary additions. And I don't think we've not seen a proprietary addition.
Great. Well, so I think a lot of people are interested in data science these days for a lot of the reasons we talked about. All the assets around us are generating data now. And so there's just a playground for people that are interested in different kinds of things to start hacking on projects and stuff that they're passionate about, whether that's music or it's sports or home automation or whatever. People are starting to get into it. What are some resources that people can look at to start getting more involved with data science?
One of the things, as I mentioned earlier, is that there are a lot of things which are open source out there. I absolutely recommend people look at websites like Kaggle, competitions. They go through, if you even are just online, you can see people's data science blogs. You can see subreddits dedicated to that in machine learning. And one of the things I also make sure to keep up, but it's an evolving field, as I said, like it's newer. You need to be keeping up on what's changing, what's happening, like with, for example, on archive.org, you have machine learning papers always coming out and new techniques that are worth keeping up with. And also a lot of new resources coming out every day. Right now, one of the big changes is we're having our first data science courses being put out by larger reputable universities, which is brand new. Now, we still had some degrees coming out from smaller, especially online universities and things like that early on, but it's something that's going to be rough at the start and then it's going to keep evolving. There are definitely statistics resources out there, books and things like that people should familiarize themselves with, especially at the theoretical level. Mathematics, there's a lot in there to learn the basics of and get a feeling for, as well as computer science, understanding some of your basic graph theory, machine learning, and you definitely want to find resources on linear algebra, basic linear algebra, I would say, is something that comes up a lot. So because it's just a culmination of a lot of different things is big idea, and then big part of it is just practicing and going through these projects and seeing what has been done before and trying to keep up with what's currently on. Like things I've seen things change over the last year or two of what resources are relevant. Like when I was in grad school, TensorFlow came out, and that wasn't a thing. And now really PyTorch, for example, if you're listening today, that's going to be one of your premier tools for machine learning. That's entirely, again, open source, which is pretty amazing when you think about it. And where you can just kind of get on there and start using deep learning right off the bat. If you're new, scikit-learn, another great package that's important to know. NumPy, which is related to Python, which is related in many ways to C-like structures, not like Python, which is a C-based Python going on there. Very key library. So understand pandas is another big one for data frames that people should experiment with. Yeah, and then there's several plotting ones like Seaborn, MATLAB.
Yeah, Matplotlib.
Matplotlib.
I think from like the engineering side too, and that's just where my brain lives because that's my background. I'm kind of like a kinesthetic person, right? Like I like to do it, and that helps me to understand. So I think all of the things that Dan has been mentioning that are related to software libraries, like one of the most powerful resources is just searching GitHub, right? And seeing what projects are out there and kind of playing with those and helping to get familiar with like pandas and TensorFlow. That's really helpful. I think also to like being a kinesthetic person, there's an MIT website called Elegant Neural Network User Interface, and they abbreviate it ENNUI. But you can like drag and drop layers and drag and drop like activations and train models, and it kind of like there's documentation, but you also can see it visually, which I found to be really helpful learning as well.
Oh, that is cool. Yeah. I mean, as I said, like there are just tools coming out all the time, and being active, looking, trying to join communities, really fundamental aspect to this. Right now, universities are behind. You can still learn some great fundamentals, as I said, with math and statistics, computer science. Great to learn conceptually and build up a good foundation because they change how you see problems, and a good place to try to learn how to learn. But if you want to be up and go the data science route, I'd say those are some of the most important things.
Yeah, and Kaggle is one of my favorite resources too for experimentation. You can get on there and do the tutorials, and they have basically competitions. And you can actually, if you get good enough at it, you can win money. So companies will put challenges up there, and you can apply different techniques and submit your solution. And if you do well enough and you win, you can get like real money.
Even if you're not a top performer, I will say quickly about Kaggle, you're still building up. You can still build up a GitHub library, like a GitHub resume or portfolio.
For sure.
Totally right about that.
Awesome. Well, Dan, Ellie, this has been great. Thank you so much for coming on, and I hope to have you on again very soon.
Yeah.
Thanks, Josh.
Awesome. Thank you for listening to this episode of Planes, Trains, and Tanks. If you enjoyed this episode, please consider leaving us a review. To learn more about Shift5 and our products, visit our website at shift5.io or follow us on LinkedIn and Twitter.